Okay, so we have this rubidium hydroxide, and I want to know what its pH, pOH, and hydronium ion concentration are. Okay, so which one of these can we answer without doing anything?
Let's see. What was it?
We know it's a base.
Mhm.
Wasn't a question, but you're right.
Yeah, which one we don't have to really do much or anything at all.
Is it the pH that we don't need to look up?
Nope. Nope.
Then it'll either be the H plus concentration or pH.
We weren't asked. Oh, we were asked that H plus hydrogen.
Yeah.
That's my bad. I thought I was going to ask you for the hydroxide ion concentration. So we do have to do a calculation. But if it asked this question, we wouldn't have to do any calculation at all. Why?
Which question? Oh, B.
Why is that the case?
We know because it's a strong base, it fully dissociates. Yeah, go. You beat me to it.
So we know that the rubidium and the hydroxide are going to fully separate. So if it's 0.00004 molar rubidium hydroxide, that means it's 0.00045 molar rubidium, and then 0.00045 molar hydroxide. So because it's a strong acid, I immediately know what the concentration of hydroxide is. All right, so how do we get the what do you want to calculate next?
pOH.
Okay, so negative log of 0.00045. What's that get you? Before we do any calculation, can you look at that and tell me what numbers it's going to be between?
Between 3 and 4.
That's not terrible, except it's terrible. Why?
Oh, fantastic.
What?
Wouldn't it be between 4 and 5?
It's not terrible, but it's terrible.
Okay.
What are we talking about?
Our self-esteem.
I'm trying to get rid of it. We're talking about a base, right?
Yes.
You're giving me pH concentrations, right?
Oh, God. So it would be between 14 and 15? No, because that's so 13 and 14. That's a base.
True. So we're okay with it being between 4 and 5 for the pOH?
I thought you said that's not good because it's an acid. Or that would be an acid, but we're dealing with a base.
1, 2, 3. So 3? 5?
3, 3.
And then what's that translate into pH? Super easy calculation.
N.65.
11.65. And then even easier, what's the ion concentration for for H plus or hydronium ion? No calculation necessary.
10 to the 11.65.
Really close, but not.
Negative.
Negative. So then we can write this. So these make sense, right? That this concentration right here is much, much lower than that concentration right there because they're inversely proportional to each other. And same situation with these guys. Right? No? Yes? Maybe?
Can you explain the pH number, please?
Ooh.
That's the whole thing.
Oh, okay, I got it.
So if I know that's 3.35, then you're good. Okay, so
Wouldn't that make it 10.65 because it's out of 14 instead of 15?
it would. Thank you. 10.65. Okay, so how about this next one? Would a solution be acidic, basic, or neutral if you mix those things together? Okay.
Neutral.
Yeah, I think it's neutral because I've got 10 milliliters
You
of
have a strong acid
2
and a
molar
strong base.
base, and I've got 5 milliliters of 4 molar acid, and they're both strong. So I have half as much, but twice as concentrated. I've got twice as much, and I have half as concentrated. So then this OH concentration would be equal to, I don't know, what would that be? 0.002, and this would be 0.002. It would be moles. So they would cancel each other out. And what would you have left in the water?
Yeah. Oh, that's what I wrote. Never mind. 0.02 moles of H plus ions or hydronium ions, and then 0.02 moles of hydroxide ions.
No, because these guys would come together to make water. So there wouldn't be any of either of those left. There would be no acid, there would be no base. It would turn into water, and then what would be left behind would be aqueous sodium nitrate floating around. Because when you mix an acid and a base together, you get what two things?
Oh, water and salt.
Water and salt. What is the H plus ion concentration of 0.2 nitric, and what would the OH minus concentration be? Okay, so it's nitric acid, so it's 0.02 molar. Just a sec here. There we go. So it's 0.2 molar H plus ion concentration. We all good with that?
Yep.
And so how do I get to the... There's a couple ways you could get to the hydroxide ion concentration, but what do you want to do?
Hmm.
Would it happen? No.
Do we remember what this equals in water?
Seven.
So if this one is 0.02, then you can just solve for the hydroxide ion concentration, right? E negative 14 divided by 0.02. So then this works out to be 5 times 10 to the negative 13th molar. All right, identify acid-base, conjugate base for the neutralization of potassium hydroxide and bromic acid. Okay, so I've got KOH, and I've got HBRO3. On the other side over here, I've got water and KBRO3. So who has to be the acid?
HBr, or I'm trying to
Yeah,
remember the name.
H-bro.
H-bro is the acid. The base is
Co.
And then what about
The conjugate acid is water, and the conjugate base is
how come the conjugate acid is water?
because it gained. It gave away an H ion, or no, it received the H ion.
Also, it's the only thing over there with hydrogen, so it's the only thing that could give a hydrogen.
Oh,
So what am I circling in the next one?
P, lowercase p, capital H.
The rest of these make chemists very sad and kind of like pukey.
Yeah, they just kind of look wrong.
I see both of these written frequently.
Really?
This one means nothing. This one means philosophy, and this one means nothing.
Philosophy. I think.
Like PhD. Okay, find the acidic hydrogen in citric acid. Okay, so we've got 1, 2, 3, 4, 5 carbons in a row. OH, OH, O. Okay. So which one of these guys are acidic?
The ones on either side.
This is.
Yeah.
This is. Anything
Yeah.
else?
The middle top one.
That one is. So anything where there's an H, then an O, then a something that's doubly bonded to an O, that H will be acidic. So this structure here, which is the same structure we had for acetic acid, that's an organic acid that we're going to talk about when we get to organic chemistry. That's the organic acid functional group. As far as the actual acidity of which one's the most acidic, the ones on the ends are more acidic than the one in the middle, but barely. And the ones on the ends are equal to each other in their acidity.
So if we're looking at an atomic structure, if it has that like classic acid chain, the H to the O to anything to another O, does it have to be hanging off of the side, or can it be in like the middle of a structure?
Since it's hydrogen, it has to be terminal.
Okay.
Okay, so what do we got for this warhead thing? What'd you find?
Malic acid and citric acid have a lot of H plus ion possibility, and there's a lot of that stuff on each candy. There's a high concentration of the acids.
They also have ascorbic acid or vitamin C.
Yeah.
So obviously warheads are a health food, right?
Yeah.
Phthalate acids.
It's got vitamin C in it.
That's all you need.
So there are 3 acidic hydrogens on citric acid. I think
I think 2
there
on malic.
there's 2 on malic and 1 on scorbic, or is it 2 on scorbic?
I'm fairly certain it's just one.
Yeah, it's just 1. So that leaves us with 6 H's coming off. So of course that thing's going to taste phenomenally sour.
Yeah.
Okay, was that it? It looks like it's it.
Yeah.
All right. Okay, what Those are notes. There. No. 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 No.
On some starbursts.
Notes. 22. No. 23. Acid base. All right, so where were we? We stopped. We didn't talk about salts, did we?
No.
Minter.
So the last thing we talked about was okay. Let's share that. Screen 2. So we briefly discussed this list, right?
Yes.
We talked about the Ka and the pKa, but we didn't get on to pH changes for ionic compounds. Okay, so wait, I feel like we did. We had a conversation.
We did. I think we kind of left off after the we'll have the pH change.
We talked about how table salt cannot change the pH, and that's where we left it. Okay, so does anybody remember the reasoning why table salt can't change the pH?
Did because it didn't have the like elements required to change the pH, or because it does break down all the way.
Sorry. It makes more sense if I write an if there. So can we answer these questions?
If I was a base, I would be. If I was an acid, I would be.
It would be sodium and the hydroxide.
Okay. So you would be NaOH.
Mm-hmm.
And what about the chlorine?
Maybe would stick with the hydroxide or the hydrogen.
Hydrochloric acid.
Okay. Hydrochloric acid.
What do you know about both of these substances? What do they have in common?
They're both strong.
They're both strong. So what does that mean to us?
It means they're gonna be breaking apart in the water anyway.
Okay, so for a salt to change the pH of water, it would need to connect to its alter ego to turn back into a base, or to turn back into an acid. So can sodium do that?
No.
No, because its conjugate is sodium hydroxide. So sodium hydroxide doesn't want to be sodium hydroxide in water. And what about hydrochloric acid? All right, I'll be right back. I have to save a dog from my daughter.
Gone.
Party time.
Party fiesta. I got starburst.
Does anyone have any idea what he's talking about?
Yeah, it's that if you have the sodium, it's gonna mix with the hydroxide, and in water, it's not actually gonna be sodium hydroxide because it's gonna be floating around.
This chapter is really hard. It's giving me trouble.
Okay, so Is this going to happen? Is hydrochloric acid going to be formed from chloride ions?
Mm-mm.
No.
Because if it did, what would immediately happen? It would immediately dissolve. So no, it's not going to happen. So what would I need for a salt to actually change pH?
It needs to be a weak
Acid or
weak
base? Yeah. So the resulting substance needs to be weak because that means it wants to stay stuck together. So let's go back over here. Why am I not here? Here. There it is.
Here, there.
There it is. All right, so let's see. Strong as Strawny and is
Strawny.
I
what?
think your handwriting. Maybe your handwriting.
I'm the Strawny man.
Oh. Oh no, that was definitely a G. Come on.
Mm-hmm.
Whatever you say, Professor.
Right?
She happy.
No? You guys don't have me here? I can't for some reason scroll over. In no way will it let me scroll over. There we go.
Whoa. It's like neon light.
G, Y, what do we think?
I'm looking and I can't see anything.
All right.
That's a G.
That's got to be a G. I mean, who
It's definitely a G.
draws
Oh.
their Y's like that?
Yeah, but the top
do.
is open, dude. And I do. Well,
No,
I loop my Y,
But
but.
that's a Y. Come on.
Ew, that's
two-
a disgusting
Two
Y.
straight
I
lines.
draw when I'm writing. I do a lot of cursive letters, so my Y's are kind of curly.
Yeah, Y's got a curve, dude.
Crazy.
You're crazy.
Rob, I think it's just because we both have terrible handwriting.
You
Yeah, it's that. It's that. It's definitely
you eat unsalted butter. So
I know.
that. No, we're not talking about butter. We're not talking about butter.
Fired. Excuse me.
and Gage can't drink soda water unless it's full of sugar.
We all can't be you, Mr. Kolbasich. I'm sorry.
I know. Okay, so what happens here?
On the reaction?
Yep. Tell me what's going on.
NA is separate, or NaF is separating into just Na and F. It's a decomposition
No,
reaction.
it's not. Not decomposition. Because no new substance is formed. It's just dissolving.
This is just
Oh yeah.
But the arrow is only going one direction, right?
Mhm.
How come?
Because unlike the second reaction, the first reaction isn't really like trying to reach an equilibrium. Or no, I think it was like there's way more Na and F than there is NaF.
No. Anybody else? What do you know about Group 1 metals? Nothing. We know nothing about Group 1 metals.
I know
Zero.
they're metals.
Oh my god.
They are always soluble.
Mm.
So of course that just goes one direction. It wouldn't come back because it can't. Sodium dissolves whatever it's attached to. So I got an arrow going one direction. And now what's the sodium going to do?
It's gonna be floating.
It's going to do absolutely nothing. Why?
Nada.
Because it's not reactive.
Because of this right here. We just talked about why. Because it can't grab an OH because it is the salt of a strong base.
Just only need one D for nada.
Really?
Yeah, NADA is nada.
Okay.
This is really doesn't do anything. Okay, but what about this fluoride? What do you know about its solubility?
It's not so, or it is soluble in water.
You don't know anything about its solubility, right? It's not on that list. Chlorine, bromine, and iodine were, but fluorine wasn't. But if it was an acid, what acid would it be?
Chloric.
What do you know about this acid? Yep.
Was it strong? It was strong.
It's not one of the 7 strong. So it's weak. So does this want to be floating around in water by itself?
Mhm.
No, it does not. Why? Because it wants to be hydrofluoric acid. Why? Because hydrofluoric acid is a weak acid, which means it wants to be stuck together, which means it doesn't want to be pulled apart, which means if it was pulled apart, what does it try to do?
Get back together.
It tries to pull itself back together. Okay? When it pulls itself back together, what is the result in the water?
Higher pH.
Higher pH because you produce hydroxides.
Because
So-
it's going to grab on hydrogens.
I threw some salt in the water, and what happened to the pH?
What, table salt?
No, this sodium fluoride is a salt. I threw this salt in water, and what happened to the pH? It went up. So these guys up here, what would you call all of these things?
Bases?
Sure,
No.
but they're
Polyatomic.
polyatomic ions, right? Just the circled part. So if I take all of these H's and remove them and put sodiums on them, when I put any of these things in water, what happens? The pH goes up.
Because they're not going to break apart.
So what we can do is say that this thing right here, this fluoride, if that thing came off a weak acid, then this is going to happen. And then that's going to happen. So tell me which anions aren't going to change the pH of water. We already know one. Give me one.
Na.
That's a cation.
No.
Chlorine, right? We already talked about chlorine. What else? Same column.
Bromine.
Bromine, same column.
Iodine.
Iodine. And then what else?
Germanium.
Nitrate. Hydrogen sulfate. Perchlorate. And chlorate. So what do these guys all have in common? Man, that's terrible.
They're green.
What do these things all have in common?
All anion.
Anything else?
Aren't those all when you have hydrogens in front of them? Aren't they all strong acids?
Correct. These are the anions of the 7 weak or 7 strong acids. So none of them will accept a hydrogen to turn back into the acid, which means they don't mess around with a water molecule. Can you give me the cations that don't mess around with water molecules? You already know one.
Lithium. I mean, sodium.
Sodium,
Lithium.
lithium, potassium, rubidium,
Rubidium.
cesium. So if any of those go into water, they're not going to mess around with the water molecule and yank an OH off of them. So tell me about all the rest of the anions and all the rest of the cations. They're all from weak acids or weak bases, so they're going to mess with pH. So as long as you remember these ones here on the left, the anions for the acids and just group 1 metals, you know that pH is going to change if it's not one of these. Okay?
Mhm.
All right.
Did you say pH was or was it going to change?
None of these things here on the left can change pH, which means everything else can change pH.
Okay.
It would need to be dissolvable. It has to be soluble for it to change pH. So if it doesn't dissolve, then it doesn't matter. Okay. So what does this word mean to you?
Like a break?
A break?
Something to something to stop something?
Okay.
Like something to stop interactions?
Okay. That's a pretty good answer. Can somebody give me an example of a buffer? In any context.
Oh, the lines that you put on the bowling alley, like the gates on the sides, so your ball doesn't go in the gutter.
Okay.
I was thinking like a piece of land or something to separate two areas.
Video buffering? Yeah, so video buffering means like if you're watching some event, you're actually seeing it probably 5 to 10 seconds later than it's happening, because if your internet slows down and can't keep up with the speed of the streaming, then you've got 5 to 10 seconds worth of playback that will just continue to happen while you lost internet connection. And then when the internet connection comes back, if it comes back within that 5 to 10 seconds, then you don't notice that there was a loss. So video buffering is buffering from a loss of continuity in whatever it is that you're watching. Can somebody give me something else?
The things you use to make your car shiny?
No. That's a no. Just going with no.
They're called nose?
What?
I think someone said a cold nose.
I don't understand.
I don't either.
Oh, you said they're called nose, so they're called nose.
Oh my god.
Nice.
I was thinking like something used to separate land.
What about that? What's that thing called?
A moat.
A moat.
No alligators.
So you don't know that.
My alligator
Castle?
senses are tingling.
Yeah, you don't know. My wife showed me a video of somebody who created a remote control boat that just looks like a crocodile head.
That's pretty smart.
And everybody was scared to death of it, like trying to get the hell out of the water, except this one guy. There was somebody trying to get out of the water, his friend, and he was already on the shore, and he actually came down with like an atomic elbow on the top of its head. It was hilarious. Like, you know that's a good friend who's willing to jump into the water with an alligator, giving it an elbow.
What was this, Louisiana?
Certainly.
That sounds like something that
So-
it's probably just doing regular.
Before Ethan tells us to move along, tell me what this has to do with buffering.
It's keeping the castle safe.
Okay, so it's stopping something from happening. That's what a buffer does. It stops something from happening. So, what about a jacket?
A jacket keeps you from getting cold.
Stops you from losing heat, right?
Stop
So a
keeping-
buffer stops something from happening. So what does this have to do with what we're talking about in this class?
Are there buffers in chemistry?
Yes. What does it have to what do buffers have to do with what we're talking about?
Are there buffers to like acidic and basic reactions?
Okay.
Maybe, I mean.
So how would that apply? Where's the buffer situation? Again, what's a buffer do?
Stop something from happening.
Oh, this would
and
just
what
like
do
keep the pH constant despite like how much stuff you put in, like acids and bases.
So the buffer says, okay, here's the pH we're at, and I want this pH to stay the same. It's not about speed, it's about simply not letting the pH change. So in a buffered solution, when an acid or base is added to the solution, the pH doesn't really change. You okay with that? The thing that it's stopping from happening is it's stopping pH from changing. You think that's
So even if you're adding an acid, the pH won't change?
it changes so minor that it's not really that important. So why?
So,
Go ahead.
I was gonna ask, what can we use to do that?
Okay, lots of stuff, but we'll definitely talk about that. But why would that be important?
Be like biological systems.
What about them?
Well, like no matter what the amount of bases and acids that are inside your body, the pH isn't going to change. Doesn't
You
know much.
you need them to not change, right?
Yeah, because if it changes, it can do something really bad. Or,
Like
make stuff not work.
like the person not working anymore because they're dead.
Because they're dead.
Yeah,
So
'cause, like all the enzymes that are used to a certain pH just stop working.
So if you're spraying down a window with Windex and you accidentally like you spray it and you walk into it, that mist of Windex, and you breathe that in. So that's a base. If you didn't have a buffer, breathing that in would kill you. But we've probably all done something like that. Walked into like a cloud of bleach or something like that
Yeah.
and smelt it, and it's gotten into our mouth, maybe made you cough or whatnot, hurt your throat. But if we didn't have a buffer in our bloodstream, something that insignificant could kill you. Okay, so how do we build a buffer? You need a way to absorb H pluses that get added to a system, and you need a way to absorb OH minuses that get added to a system. Okay? It's got to be able to do both things.
So what exactly do you mean by absorb?
Means if it goes into the water, it's got to be immediately removed.
Where would it go?
It would attach to something that doesn't want to let it go.
Okay.
So whoa, not that. If this was in the water, floating around, okay, and an H plus was added to the water, what would this fluoride do?
Attached to it?
And you'd make hydrofluoric acid. So free H plus is what changes pH. Is the pH or is the H plus free?
No.
No, it's connected. Okay, so pH didn't change because it connected to this F minus. We okay with that?
Mhm.
But now we have hydrofluoric acid.
But
So-
hydrofluoric acid's a weak acid, so it stays stuck together.
Oh, okay.
So tell me what happens in this situation. How many times can I back up? There we go. Enough.
Back it up, back it up, back it up.
So
What happens this if I've got chloride and H plus gets added to the system?
It forms hydrochloric acid.
Anybody?
No, the solution
It
stays
forms-
acidic.
Nothing happens because
Nada.
these two things together is a strong acid. So even if they did connect for a moment, what would they immediately do?
Disconnect.
Disconnect. So was I able to change the H plus ion concentration by adding chloride? No.
No.
No, because this H plus is still in the water because it never made HCl. This is not gonna happen. We all right with that?
Okay, but then now there's more H pluses, so doesn't it become more acidic?
It does. So chloride is not a buffer. That's what I'm trying to point out.
Oh. Okay.
Fluoride will buffer, chloride won't. What else
Okay.
won't?
BR.
Those ones there in yellow. BRI, nitrate, hydrogen sulfate, perchlorate, and chlorate. None of those can buffer because they don't let anything attach to them.
Okay. So then how do we create hydrochloric acid if it doesn't want to attach?
That doesn't have anything to do with what we're talking about.
Okay.
All right, so so let's talk about this. What happens if this goes into water?
It fully dissociates and becomes aqueous.
Yep, I'm gonna get a sodium and a sodium and a carbonate with a -2 charge on it. What's the carbonate gonna do?
In the water, it's flowing in it.
What's it gonna do to the water?
Oh,
Make it more basic?
Yep,
Or
because the water molecule is going to be here. It's going to grab one of those H's off. It's going to turn back into HO3 with a minus charge and leave behind a hydroxide. What's going to happen next? This guy is going to grab another H off another water molecule and leave another H plus behind. And then I'm going to have carbonic acid. That is a weak acid. So I just generated 2 OHs by adding this salt to this. But let's say that I put these guys in the water. Let's say that I had HCO3 negative floating around in water. And some acid got added to the water. What would happen? The hydrogen carbonate would grab the hydrogen ion and become carbonic acid. So what happened to the concentration of H plus in the water?
It went down.
Okay, it went up for a moment and then went back down to where it was before, right? So it effectively countered that. So it effectively buffered this H plus addition. So you can talk about that anion being able to soak up excess H's. This equation down here is something we're going to use a lot. Let's go through the derivation of this. This is called the Henderson-Hasselbalch equation. Okay, so are you okay with this first equation here? What is that?
Are these like, what is the H?
I don't. What do you mean? It's hydrogen.
What
ion.
does, oh, it's hydrogen.
What you should be asking me is, what is the A?
I thought the A represented acid, but
No, the HA represents the acid. The H plus represents the hydrogen ion. What's the A represent?
the hydronium ion?
Conjugate base.
In this case, a conjugate base, but it represents the anion of whatever acid we had before, right? So I have this acid here, this weak acid. How do I know this is a weak acid?
Okay, that's because it has the back and forth arrow.
Because it's got the back and forth arrow. That's telling me it's a weak acid. So then this is the H that comes off, and this is whatever the other piece is. It doesn't matter what the other piece is. It could be, whoa.
Oh, we start?
It could be any of these anions. It doesn't really matter which one. It could be any of these ones down here we didn't circle. But it just needs to be an anion of a weak acid. Okay, so, and then what do we call this thing here?
The acid, well, no. The whole equation?
Yep,
Isn't it just the Henderson-Hasselbalch equation?
it's not.
Oh.
Anybody? Really?
The acid dissociation constant?
Okay. And then what's the that's what the thing on the left is that I drew. What's the thing on the right? No, not a buffer. It was from last quarter. What's this thing here mean to you?
Oh, is it a change of something? Or the
I'm gonna forcibly unmute all of you to see if you're just watching Netflix.
Is there reaction speed?
It's an equilibrium constant. Right? Ka is the equilibrium constant. This thing that I have circled is the equilibrium expression for a weak acid. Any weak acid. I know it's an equilibrium constant for a weak acid, one, because it says Ka, and two, because one of the products is an H+. So I'm just going to take that expression and I'm going to rearrange it. So below, there was just a tiny bit of algebra done there. Everybody okay with that? What would happen if I took the negative log of this thing here? Negative log is equal to pH. What would happen if I took the negative log of the Ka? That becomes the pKa. What would happen if I took the log of this fraction? It would be negative instead of positive. So to make it easier, all you need to do is flip the numerator to the denominator. So what you can see is the acid became the denominator here, and the base portion became the numerator here. And to do that mathematically and legally, mathematically, is I change the minus sign here to a plus sign. Why does that work? Because I'm taking the log of something, right? So if the log is 10 to the negative sixth, I can make it 10 to the sixth by my answer being plus or minus. Because 10 to the, say 10 to the negative 4 times 10 to the negative sixth is 10 to the negative 10th. Are we okay with that math?
Yeah.
It's just, I don't know what that is. Math 111 stuff, maybe.
So are you just taking like that whole equation, the top one, and just
Taking the negative log of each term. So this H is a term. And then this Ka, I turned it into a term. I guess I'm not taking it of each term. I'm taking it of the things that I want to. So I take a negative log of this hydrogen ion on the left side. Then I take the negative log of the Ka, and I separate it out by taking the negative log of the fraction. And when I do that, I separate it out by an addition sign. Why an addition sign or a subtraction sign? Because I took the log of it. And what do I do to exponents? I add or subtract the exponents of things when they're multiplied. And they're multiplied up here, but down here, they're added and subtracted because I took the log. So what I end up with is pH is equal to the pKa plus the log of the base, which is the anion, divided by the acid concentration. If I was talking about a weak base buffer, this would say POH, and this would say PKB, and then this would say acid on top, and it would say base on the bottom.
wait, why are those flipped? Oh, because they're flipped beforehand in the other.
Okay, so we'll do a really, really simple one here and say a buffer problem can be super simple, or it can be much more complicated. So if you're being told to calculate the pH of a buffer, and you know that the pH of, so let's say that what you need for a buffer is you need, say, a weak acid plus salt of weak acid. Okay, so this first part's easy. So I'm going to say we've got CH3COOH. So that's acetic acid. So great, I got a weak acid. What do I mean by salt of weak acid?
The ionic or one.
I take the H off and I put a sodium on. And now I've got the salt of a weak acid. I need those two things. Okay?
And that's just for the bottom number, or not number, but whatever it is.
No, it's for every buffer. For any buffer that I'm creating, I'm going to use a weak acid and the salt of that weak acid. So which one of these two things, this one or this one, is going to be considered the acid?
The one with the H.
Okay. Why? Because that's acetic acid, so that's the acid. Why is this one over here considered the base?
Because it doesn't have that H to give.
That's not a horrible answer, but it's not good enough. What happens when this CH3COONA goes into water?
The Na disassociates.
All right, so I've got a CH3COO with a negative sign, and I've got an Na with a plus sign. What does the Na do in the water?
Nothing.
Does nothing, right? Does absolutely nothing. Oh my God, it's driving me crazy. So this does nada. But what does this do?
It changes the pH.
So it finds itself a water molecule, turns itself back into CH3COO negative, sorry, COOH plus an OH minus. So it changed the pH by raising the pH because now there's an OH in the water that there wasn't there before.
So it becomes more basic.
So it becomes more basic. So that's why this is the base, because it's doing that to the water. So I put an acid and a base in the water. So what ends up happening?
It's a buffer because they just counteract each other.
They counteract each other. Okay. So a quick calculation for this. How do I figure out what the pH of this buffer that's given to us in this problem? So I was told that I've got 0.75 molar acetic acid and 0.5 molar sodium acetate. Awesome. Okay, so I need to know the pKa. And so let's go up to find acetic acid on this list. So it's at the top. So the pKa for this is 4.76. Looks like I typoed it or looked at a different list. Doesn't really matter. So so there's my pKa. And so then I'm going to punch in the concentration of the acetic acid as 0.75 and the sodium acetate as 0.5. I'll take the log of that and then add it to the 4.75 and I get 4.57. So what this means is this buffer is going to buffer at a pH of 4.57. All right, great. That's all that matters, that it's buffering at that pH.
So was that the original pH of the solution?
No, the solution was water.
Oh,
And I added these substances to it, and now the pH is 4.57. But what is this buffer going to do?
bring it back up to the normal pH?
Oh, no. This is the new norm. I made a pH for a buffer that buffers at 4.57.
Made a pH.
Why would I want to do that? Why would I want to make why would I want to make a solution's pH 4.57?
Well, it's more acidic because you want to make the solution more acidic.
Sure. And why would I want to make the solution more acidic? Anybody take a microbiology yet?
No, but I could guess that you either have an enzyme or something that works at that specific pH. You want to keep it there.
Yeah, so the microbes have to have particular pHs, and they're not all our pHs. So if you're trying to grow a particular strand of some kind of bacteria or mold or even virus, and it lives at a pH of 4.57, you better make a solution who's being buffered at 4.57 for the pH. Because then when acids or bases are added, the pH stays 4.57.
I thought buffers are supposed to keep the original pH.
The buffers are supposed to buffer at whatever pH they're supposed to buffer at.
So you have water originally.
Yep.
And you add an acid and a base.
Yep.
And now the pH is 4.57.
Correct.
I just like I don't understand.
The thing that's not going to change is the 4.57. We were trying to make a solutions whose pH was 4.57.
Okay.
Are you sad that it's not a pH of 7?
I'm not sad. I'm just confused because buffers are supposed to keep. So are buffers supposed to change to a specific pH, or are they supposed to keep the original pH of the solution?
The buffer itself has its own pH.
Okay, when we say buffer, it's an acid and a base acting together.
A weak
right?
acid and the salt of that weak acid acting together as a buffer. So I need this weak acid and I need this salt of this weak acid. And then they'll buffer at whatever pH you set up.
Okay.
We okay with that?
Ish. Yeah.
Okay, let's do. I know Annika's really the only one talking, but nobody else is saying anything either. So, or nobody else is saying anything. So I'm guessing you're all a little confused about that, which is fine because this is a tad confusing. But let's do this. So, let's use the one that we have for our body, which is carbonic acid and sodium hydrogen carbonate. So that's our buffer. All right. So if I go back over here, look at this, scroll back up to carbonic acid. So carbonic acids, it buffers at a pH of 6.35. Its pKa is 6.35. Okay, so let's go back. So it's got a pKa of 6.35. Great. So let's say I'm going to make a solution, and the solution's concentration is, I don't know, let's say that this one is 0.75 molar, and this one here is, I don't know, 4.5 molar. Okay? So this buffer is going to buffer at some pH. We're not sure what it is until we punch it into the calculation. So pH is equal to pKa, which is 6.5 or 3.5 plus log of why am I putting 4.5 in the numerator?
Because your 4.5 is to the salt, and then 7.5 is to the acid.
Okay, so the base, which is in this case the salt, has a concentration of 4.5, so that goes in the numerator, and the or the carbonic acid is the acid, so that's got to be in the denominator. Log of 4.5 divided by 0.75 close parentheses equals. This thing is going to buffer at a pH of 7.13. That's this pH's buffer. So if an acid or a base is added to this solution, what's going to happen?
Whoa, I lost sound.
What?
Nothing. I popped my neck. If an acid or a base is added to the H2SO3 and the Na.
Yep, this solution that's now a buffer.
If you added an acid, I mean, it's a buffer, so wouldn't it just stay at 7.13?
It's going to barely change that pH. If I add a base, it's going to barely change that pH. So what was the buffer supposed to do?
Keep the pH consistent, whatever level you want it to.
All right. So this thing is going to work at a pH of 7.3. So what if I modified my starting ingredients? What if I switch these two numbers? So now I've got pH is equal to 6.35 plus log of 0.75 divided by 4.5.
It would buffer at roughly a pH of 5.6.
Okay. I got 5.7, but whatever. 5.57. Oh, you said 5.6. Yeah, that's fine. Okay, so why is this important? Why is this significant, what we just did right here on this page? I made two different buffers. There were more than an entire, out of the same stuff, out of an entire pH unit, more than a pH unit difference.
So if you make a mistake with measurements, then you could get a completely different buffer.
Okay, true. Anything else? So somebody pick a pH. Doesn't matter.
7.
Okay. Which of these buffers would be good at buffering at a pH of 7?
The moved it. Stop moving it. Chromic acid.
No. Anybody tell me why? No. Because she's picking this one that's close to 7, but it's chromic acid 2. It's got to be a 1.
Okay.
Or
Then no, it's not citric acid. Carbonic acid.
the carbonic acid. What pH does your body buffer at?
7.4-ish.
7.4-ish.
Ish.
So if you had the choice, which of these would you use to buffer?
Carbonic acid.
Carbonic acid. So
Copernic.
if your concentration of the salt and the base were exactly the same, what happens to this term here? Let's say the log of 1 molar divided by 1 molar. What's this turn into?
1.
It's 0. Are we okay with that math?
Yeah.
Mm-hmm.
Okay, so if I'm going to take the log of 10 to the third, what's my answer?
3.
3. What if I'm taking the log of 10 to the 0?
0.
So 1 is equal to 1 times 10 to the 0. We okay with that?
Yes.
This right here is 1 times 10 to the 0, so my answer is 0. So if I make my base and my acid concentrations the same, then it buffers at a pH of whatever the pKa is. So then what I can do as the user is I can increase and decrease the acid and base ratios until I get to the pH that I want to buffer at. Does that make sense?
Yeah, sort of.
So if I want to buffer at 7.13, there we go. This needs to be 4.5 and this needs to be 0.75. So the nice thing about go ahead.
Sorry, what is the pKa of? Is it the first or the second?
The first one. I mean, you can get the pKa of any of them, but it's just the K, the negative log of whatever the Ka is. All right, so let's look at what happens if I put an acid or a base in just pure water and see what happens to the concentration. So somebody calculate that. Everybody calculate that first one. If 40 milliliters of 0.25 molar sodium hydroxide is added to 550 milliliters of water, what's my resulting pH? So this is a small amount of base added to, and the concentration of the base is low. It's only 0.25 molar. I want to know what happens to the pH when that's when that small amount of sodium hydroxide is added to the water. All right, I'm gonna give you a couple minutes.
Yeah.
Okay, hang on. And mm,
We got it?
I'm having trouble with the part of the equation that's the parentheses where the top is the salt of the conjugate added and then the bottom is acid, which I'm guessing would be the base.
This is not a Henderson. There's no buffer here. This is just water.
Okay.
So this is sodium hydroxide, right? So it's going to go into water and turn into sodium and then turn into hydroxide. So what's the concentration of the hydroxide?
0.25 molar.
Okay.
Of the hydroxide, sorry.
So this is molar. So this is mole per liter. And I've got 0.04 liters because it's 40 milliliters. So 0.25 times 0.04. That gives us 0.01 moles of OH, negative. Awesome. So I'm trying to calculate the pH. So I need the negative log of the H plus ion concentration, or I could use the negative log of the OH minus concentration and then subtract from 14. But I still need the concentration in moles per liter. What I have is moles of OH. What am I going to divide by here?
$509 liters. Or I mean, milliliters.
Yep. 0.59 liters. So divided by 0.59. So I get 0.1695 as my hydroxide ion concentration. So if I take the negative log of that,
Is it a 695? Or 605?
0.1695. I get a pOH equaling 1.77. So my pH is going to be 12.33. 12.33? 12.23. All right. I forgot to lock the door. You can't be in here. I know.
Aw.
Okay, so yep. Okay, so what happened to the pH of this water when I added this dilute sodium hydroxide, a small amount of dilute sodium hydroxide?
It decreases.
It went up by more than 5 pH units, right? So that means it went up by more than 100,000. It's 100,000 times more basic. You okay with that?
pH 100,000.
Okay, so what if instead we added it to an acetic acid buffer solution? So the first thing we're going to need to do is figure out what the pH is of the acetic acid buffer solution before any sodium hydroxide is added. So then pH is equal to, what is it? What's acetic acids? 4 point something, 4.76. So 4.76, not times, plus the log of 7 molar divided by 0.04 molar. 4.76 plus log 7 divided by 0.04, close parentheses, equals, this will make Annika happy. This buffer buffers at a pH of 7. Okay?
Okay.
So now what happens if I add this sodium hydroxide to the solution? What are you expecting to happen?
It'll get closer to 7.
It already is 7.
It'll stay at 7?
It'll stay really close to 7, right?
Mm.
But it's going to change, and we're going to have to show how much it changed and show the calculation for how it changes. So let's, let me do, one sec, that, skipping tool, new, I'll grab this. Copy, go here, add a new one of these pages, and then put it down here. Whoa, too big. All right, that's good. All right, so what we're going to try to figure out is what happens to the pH of this solution now that it's a buffered solution. So what we're expecting is the pH isn't going to change very much. Great. So let's prove that the pH isn't going to change very much. So you need to take all of these steps, and this is probably the thing that's going to not make a lot of people happy with acids and bases, but regardless, this is what you need to do. So I need to take several steps. I need to know how many moles, actual moles of acetic acid I have. I need to know how many moles of sodium acetate, or just acetate, I've got. I need to know how many moles of hydroxide I'm going to be adding to this. So we're going to go with 0.04 mole per liter, and there's 0.55 liters, and we're going to go 7 mole per liter, and we have 0.55 liters, and we've got 0.25 moles per liter, and this was 0.04 liters. This was 0.01 moles of OH. This is going to be 7 times 0.55. This is going to be 3.85 moles of acetate anion, and this is going to be 0.04 times 0.55.
Is that OH an ion?
Yeah. and this is going to be 0.022 moles of acetic acid. Okay. So then we have to build something called an ice table. So the ice table is initial, change, and then at equilibrium. And I'm going to have acetic acid here. And I'm going to put acetate here. Okay, so before I added the sodium hydroxide to the solution, I had 0.022 moles of, sorry, there's a mistake there, right there. This needs to be an H. And the acetate is 3.85. Okay, so how are these concentrations changing? They're changing because I'm adding 0.1 mole of hydroxide. So I have a buffer, and my buffer is composed of acetic acid and acetate ion. Which one of these two buffers, pieces of my buffer, is going to handle OHs?
The H on the top one?
The acid is going to handle any OHs. So that means when I put in 0.01 moles of the hydroxide, I'm going to lose acid. And I'm going to gain that exact amount in acetate, because what's going to happen is the H is going to come off, leaving behind acetates. So this works out to
And
be
then that makes water, right?
and water. And that's going to be 0.012. And then this is going to be 3.86. Is that right? No. Yeah, that's right. So then I'm going to do the calculation.
0.021?
0.0, no? 0.012.
Under the acid, why is it 0.012 if it loses 0.01?
Because it, math? I don't know.
So it starts at 0.022 and we subtract 0.01,
Yeah,
correct?
yeah.
So wouldn't that become 0.0? Oh, okay. I was forgetting a decimal place.
Okay. .76 plus log of 3.86 divided by 0.012, close parentheses, equals, and we end up with 7.2.
Ooh. So it barely changes.
It changed, but it didn't change a lot. How much did it change when we added it to 550 milliliters of pure water?
By 0.2.
No, the prior problem, when we added it to pure water.
It changed by 5.
pH numbers.
It changed by more than 100,000, which was 5 pH units, so 5 orders of magnitude. And this changed by 0.2. So did the buffer do its job?
No. Well, so that's by 0.2 orders of magnitude.
No, that's not an order of magnitude. It changed it by 0.2. The other one changed.
Yeah.
The other one changed to, what was it, 10.5 or something like that?
So then, yes, the buffer did do its job.
Yeah, this one went to 12.32, and the one we just went changed to 7.2. So a massive difference in the amount of pH change. This, what we just did right here, this calculation is how you have to calculate changes in buffer pH when you add some acid or a base to the substance.
Okay.
Okay?
So it's only for this specific type of problem?
Correct.
Okay.
How is
What?
Is it also when a base is added?
No. No.
the, is it also when a base is added? Yep.
Yeah, can it also be used when a base is added?
You can do the same exact thing. Wait, what? We did add a base.
Oh, when an acid, sorry.
Absolutely. How does the problem change if an acid was added? If this was sodium, instead of sodium hydroxide, it would say hydrochloric acid. This right here would become positive, and this right here would become negative.
Wait, I can't see anything.
Sorry.
Yeah, you're not screen sharing.
Sorry. Sorry. Screen to share. The really? Instead of losing acid, if we added an acid to this, we'd actually increase the amount of acid. This would become positive. And this guy here, we would lose some of our base. So this number would change to 4 here, and this would be 3.2. And the pH would go down instead of up. It would probably be 8.6 instead of 7.2. So let's do one more thing here. So this is the buffer that we were just talking about. So both of these are floating around in the water. If H plus is introduced to the water, that would tend to drop the pH, bring the pH down if it lasted in the water. But what would this buffer do to an H plus that was added to the water?
It would not let it change the pH
How?
by adding OH to counteract it.
No. In the notes, I use the phrase soak up.
So instead of the H being there, it's like it's not there at all.
Where did it go?
To the CH3COO.
Yep.
To
So
create
this,
another acid.
it attaches to that right there and becomes the acid. So I make a little bit more of this acid. So the pH definitely goes down, but now I'm talking about a weak acid instead of a strong acid. Does that make sense?
Why does it become a strong acid?
It wasn't. This down here is an example of a strong acid, free-floating H
Yes.
pluses.
Yes.
So what happens if OH minus is added to the water? Because that would make the
becomes-
pH go up.
The pH goes up, it becomes more basic.
Okay, but how does this stop it from going up dramatically?
Then it
It turns it from a strong acid to a weak acid.
But that's
It's
not a strong acid.
this is a strong base.
Oh,
Strong
strong
base.
base to a.
Can we clean it out first?
It
would it
changed-
attach to the acid? It wouldn't.
Who's yelling? Nobody?
Sorry, I think my parents are talking in the background.
Ah.
So what's happening here?
So the hydroxide is
This needs to disappear. So what makes it disappear?
would an H come off of the acid?
That
and then
H
it
comes
creates
off
water?
of there and it make a water molecule. Exactly right.
Okay.
So depending on what happens, if I add an OH, then in this case, the weak acid attacks the OH and turns it into water. And if I add an H, then the H gets, whatever you want to call it, soaked up, attached to the anion. And so it's not in the solution. Both of those situations, H plus or OH went into the water and they disappeared. That's what a buffer does. That work for you guys?
So does the OH minus like attract the H from the acid, or does the H from the acid?
Whatever. They run into each other and then the H comes off.
Okay.
Somebody making a smoothie?
No, my dad is using the leaf blower outside. I'm getting kind of mad.
That's
I
not
have
as
a good
much
impression of the leaf blower.
fun as
I don't.
Want to hear it?
No.
Yeah, go ahead. He's muted. He's
Good.
still muted.
That's clever.
And then
There we go.
What?
Unmuted.
Congrats. Okay. Can
Sorry?
I was gonna ask if we could do a bit more math, but I mean it's already.
I
I'm
think
just
I'm gonna
having trouble.
I
I'm
think-
not having trouble with the problem we just did, the math we just did, but the math we did before it, with the 40 milliliters and the 0.25 molar NaOH. I don't know. I was having trouble kind of understanding that equation, I guess.
wouldn't even consider it an equation. It's just if I had 750 milliliters of pure H2O and added, I don't know, let's say 25 milliliters of 0.75 molar hydrochloric acid, what's the pH of the solution going to be? So what you're trying to do is, what's the H plus ion concentration? And to get that, you need moles of H plus divided by liters of solution. Well, the liters of the solution in this case is going to be 0.775 liters. Are we okay with that?
Yeah, because there's 775 milliliters.
Okay. So what's the moles of the H plus? Well, we'd have to do a calculation. I've got 0.75 moles per liter of hydrochloric acid. And I added 0.025 liters, because that's milliliters, 25 milliliters. And so I end up with 0.75 times 0.025, and this gives me 0.01875 moles of H plus, because the liters
Can you
cancel
repeat that
out.
number again? 0.0 what?
It's on. I'm sorry. Just 1 second.
Okay.
I've been doing this math on the screen, thinking you guys were watching, and nobody was.
I was just hopelessly copying your words.
Gotcha. So there's my 750 of water, my 25 milliliters of 0.75 HCl. I figure out the concentrate, or I figure out the number of moles of HCl. And in this case, I don't care about the Cl part because this is a strong acid. It's just going to disassociate. So I take the 0.75 moles per liter and I multiply it by the volume to get rid of liters, and I'm left with moles of H plus.
H plus.
So then I can take that moles of H plus value and I can just drop it in right here, 0.01875 moles H plus. And then the math on that is divided by 0.775. The math on that is 0.022, no, sorry, 242 molar H plus. And again, it doesn't matter if I write HCl or H plus down because it's a strong acid, so it's just going to disassociate. So then if I go negative log of 0.0242, I'm going to end up with 1.6. So, I mean, this was pure water, and its pH was 7. I added this small amount of hydrochloric acid, and the pH dropped to 1.6. So that's about gastric juice concentration.
Delicious.
So, what pH did we start at?
It was pure water, so it was 7.
Oh, cool. So it dropped 5.4 points, which is
100,000 plus?
yeah, another 100,000.
Somewhere between 100,000 and 1 million.
Wow. Okay. And then that's the problem just asked for the resulting pH, so that's the answer, right?
Yep, that was it for that problem. I'm going to give you problems like that to do on the homework, and then we'll talk about it on Thursday. Did
Okay.
you guys pick up your labs?
Yes.
Yeah.
The kids?
Yeah.
My mom's afraid I'm gonna blow something up.
I'm
I
excited.
wasn't able to pick it up in those times.
Can you do it right at 5 today in Hood River? He's there from 5 to
Yeah.
6 today.
Okay.
And if not, call the bookstore and talk with either Jack or Rose, and
Okay.
they'll figure something out for you.
Sounds good.
All right, I'm booting you. Have a good day.
Okay, bye.
Thanks, Rob.
Adios,
Thank you, Rob.
everybody.
Later.